Howdy guys, welcome to another Algebra 2 video. We're going to be talking about polynomial functions today and polynomials in general. It says polynomial is an expression consisting of variables and coefficients that involves only the operations of addition, subtraction, multiplication, and non-negative integer exponents. So a single term in a polynomial is called a monomial. The degree of a polynomial is the greatest exponent on an individual term of the polynomial. So the first types of problems we're going to see, and I don't have any idea why they're numbered 3, 4, and 5. Maybe I do actually. Nope, no knowledge. That's okay. Is we're going to determine whether each expression is a polynomial. If it's a polynomial, state the degree of the polynomial. So we're looking for variables that are raised to positive powers, okay, non-negative powers. So this guy has a couple different variables. They're all raised to non-negative powers, so we would say yes. This thing is a polynomial. Okay, to find the degree of the polynomial, we're going to look for the largest exponent, and that's going to be our degree. So our degree here is 3. Incidentally, if you have more than one variable, you just add these together. So that particular term, we call this a term, each piece of this polynomial, that term has a degree of 2. This term has a degree of 3. This term has a degree of 2. And this is 0 because there is no variable. Okay. So in 4, our second example, we're in trouble because of the square roots. We'd say no, not a polynomial. And it's because of the radical symbol. Okay. What about this expression? Is this a polynomial? We've got variables raised to non-negative integers. It is. And then we're going to add these guys up. That term's degree is 7. This term is 5. This term is 1. Kind of like we did over here. This one was 3, this one was 2, this one was 2, this one was 0. So the largest degree is 7. So the degree of our polynomial is 7. It says a polynomial is in its simplest form when all the terms, all like terms, are combined, parentheses are eliminated, and fractions are in simplest form. They want us to simplify. So what we're going to do here is distribute this out in front of the set of parentheses to these 3 terms. We're going to use exponent properties to help us simplify them. We add here, that's a 1 and a 3, so it's going to be a 4. We're going to add 1 and 2. And we're going to add 1 and 1. Now we need to combine like terms, which would be these guys and these guys. Okay, that's in simplest form. Okay, we're going to do the same thing over here. Distribute this negative 5 here and here. We no longer need the parentheses here. We never did, actually. That is a, I don't know why that keeps happening. I think I'm too close to the corner. It doesn't like it for some reason. All right, we just need to combine these like terms. That's in simplest form. Okay, we're going to be asked to multiply these polynomials together. I prefer the box method for this. So this has 2 terms. This has 3 terms. So I would make a 2 by 3 box. I know some of y'all don't prefer to do that. There are other ways to multiply these, but this is the way I teach it. That's an a squared. Okay, so this box is going to be the product of 3a and 2a squared, which is 6a to the third, minus 2a squared, minus 15a squared, 5a, 21a, and minus 7. The reason I like using the box method is because your like terms are at diagonals. It's real easy to combine those like terms. That's a cube. That's a 6. Okay, let's do the same thing over here. This one's going to be a 2 by 3 or a 3 by 2, whatever you're most comfortable with. Okay, it's going to be 10y cubed, 4y squared, 30y squared. And if I'm going too fast, just pause it and catch up. And minus 14. We're going to combine these like terms. This is a 23, isn't it? Okay. I think we're in good shape there. So when you're multiplying, I would use the box method. The bigger the polynomials, the more likely you are to use the box method. Let's see. So we've got some new terms. We use 0, root, solution, and an x-intercept to talk about an x value where these cross the x-axis. Okay, so we've used these interchangeably. We're going to keep using them. Local min and local max, they're points on the graph that are higher or lower, depending on if we're talking about a max or a min, than all the surrounding points. The graph will change directions at that point. Okay, so it'll go from increasing to decreasing and so forth. Critical points are all the zeros, which remember are places where it crosses the x-axis, and local extrema. And this extrema just means mins and maxes. Okay, so in behavior, what happens at the end? What happens with the y value on the graph as the x value gets really, really big in a positive fashion or really, really small in a negative fashion, that is super negative, super high negative value, really far away from 0. So let's look at some examples. Find the critical points and describe the end behavior of each graph. So we want to do the whole kit and caboodle here. So if you graph this thing, it looks like this. Okay, so this is -1, this is 1. So what are our roots? It's a little bit smaller so you can see it all at once. Our roots are x equals plus or minus. No, it doesn't. It just equals plus 2. You know, I like to list these out from left to right just so we make sure we don't miss any. So let's do -1, x equals 1, and x equals 2. If you wanted to, you could just list off 2 of these, x equals plus or minus 1, comma, x equals 2. That's not wrong either. So our local max is going to be this guy. It's higher than any points around it. Okay? And if we use Desmos, you could calculate that point or hover over that maximum point, and it would say this is -0.25, comma, 2.1. Local min is going to be this point down here. We could hover over that, and Desmos, remember, doesn't put arrows on the ends of these things, but there should be. And really, we should label these too. This is y and this is x. That's a little bit prettier of a graph. That's my only complaint about Desmos is it doesn't label axes and it doesn't give arrows when you have an infinite curve. Okay, what's our local min? That's this guy. If you hovered over it, it would tell you that's 1.5, comma, -0.6. So for now, we're okay with just using Desmos to find the roots and the local extrema, or local maxes and mins. Let's talk about end behavior. There's a script for end behavior. We're going to write the same thing every time we're asked for end behavior. As x approaches negative infinity, we'll do the left side first. F of x approaches something, comma, and as x approaches positive infinity, f of x approaches something, period. Okay, our job is to fill in these two blanks. What happens to f of x on the two different sides? So let's talk about the left side first. As x approaches negative infinity, so we're going way out here to the left, what's y doing? It's going way down. So we're going to say negative infinity in here. On the right-hand side, as x approaches infinity, as we go way over here to the right, what is f of x doing? Y is going up. So we're going to say infinity there. All right, do this one as well. If it lets me slide it over. There we go. Okay, so we're going to start off with roots. They are, well, it's not scaled, and it should be. Let's do this. This is -1, that's -2, that's -3. Okay, so the roots are x equals -2, x equals -1, x equals 2. Oh, and x equals 0. Let's squeeze that guy in there. So it crosses 4 different, well, all those would be on the same line. Hang on, do that. Okay, so it crosses the x-axis. This graph crosses the x-axis in 4 different places. X equals 2, x equals -1, sorry, x equals -2, x equals -1, 0, and x equals 2. What's the local max? And what order you list the local max and min doesn't really matter. Local max is right here. If you hovered over that, Desmos would tell you that's -0.5, comma 1. Local min, in this case there's 2 of them. There's one right here, okay. That one is -1.75, comma -0.5, and the other one is down here. That guy is 1.25, comma -7. Okay, let's do the end behavior. As x approaches negative infinity, comma, f of x approaches, we're going to leave room for something, comma, and as x approaches positive infinity, that'd be the right-hand side, f of x approaches something, period. Okay, left-hand side first. On the left-hand side, we're going up, so we're going to do infinity. Right-hand side next. On the right-hand side, as we go to the right, what's happening to y? It's increasing, it's going up, right? So we're going to write infinity. Now, we talked about local extrema, so that's a local min. That's a local max. That's a local min, but it's also an absolute. It's an absolute minimum. It's the very bottom of the graph. Nothing goes lower than this graph, right? Nothing goes lower than this point in this particular box, right? But when you look at the whole graph, nothing goes lower than this point. That's what makes it an absolute. Over here in this example, that's a local min. But look, this arrow keeps going down, right? So there's values below it. This is a local max. But this arrow goes up. So there's values above it. So neither one of those are absolute. Neither one of these are absolute, but this one is. Okay, if you have any questions, see me for tutoring. Good luck with this section, guys.